So I'll be talking about trying to define for you what NVIDIA and we are referring to as the software-defined grid. But I think first I need to sort of talk about which part of the grid I'm talking about. And this is not about transmission or generation. This is about the distribution part of the grid. But it's really about the part of the distribution grid that I think of as delivering energy for humans. And what exactly do I mean by that? Well, we talk a lot, and there are serious and significant issues with trying to deliver an energy to machines. So massive growth in data center demand, manufacturing, and so on. But in the end, the output of these machines is going to be in service of humans that I think are going to exist for a little while longer, at least I hope so. They don't live in data centers. They are distributed all across the face of the earth. And they're experiencing sort of electrification of everything. So EVs are going to have robots in the home, any number of things like that. And utilities are trying to balance both of these needs and concerns. You have heard, I think, a little bit about, from Josh had touched on, there is this tendency to think of utilities as sort of crawling and then running. You will hear, if you're outside the industry, that they're slow moving and risk averse and so on. I would say after a couple of decades of delivering solutions to them, that's really not my experience. I find them to be quite eager to embrace new technology once it becomes available, but also when it's actually reliable and secure and cost effective. And so to kind of justify that assertion, I would like to give you 20 years of utility history technology very quickly, but there's a reason for it, which is that how we got here does affect where we're going next. So starting in about 2006, believe it or not, so literally 2 decades ago, what we were able to do was to introduce kind of modern networking techniques to the industry, sort of new RF mesh technologies, IP-based technologies combined with cellular and so on. And what used to be thought of as revenue meters that were largely generating consumption data for billing, really turned into more complicated edge sensors. And so the networks really started delivering richer data all the way to the back office. So not just consumption data, but now also voltage and power quality and harmonics and such. That would all land in the back office, and expert utility personnel would write software and algorithms to analyze that. And the output of that inference, if you will, would essentially result in truck rolls. So this goes back to the problem of this widespread, challenging physical infrastructure that needed to be managed. And what we were doing was building a telemetry network all the way out to the actual edge of the grid. So sometimes people, when they say edge, they mean substation. Sometimes they mean transformer. In this case, no, we mean the actual edge of the grid, which is the meter at the customer premise. Right. So what we have here, though, is an excellent telemetry network, lots of detailed data, but a fairly slow loop of improvement in the sense that you had to update the back office, people had to work on it, and then dispatch these trucks. Well, as happens, and over the next decade or so, what Moore's Law did is allowed us to deploy more compute and more memory at the edge. And as a result, what now happened was that this slow loop became much faster, because we could essentially take the logic from the back office and start pushing it out towards the edge, programming and configuring these edge devices to act fairly intelligently. In fact, as early as the early 2000s, we started to call this the smart grid for this reason. So what that intelligence at the edge at the time meant was that we could actually use peer-to-peer networking and such to have these devices manage the grid much more autonomously, even then. So, for example, a meter would signal an outage simply directly up to a switch and recloser. We could automatically restore power. When an EV charger turned on and off, we could detect that condition and respond depending on seasonality, time of day, and so on. Same with PV. So the issue here, though, again, is that what we could do is program and configure these devices based on known information and known scenarios. What happened next, and is happening now, with our partnership with NVIDIA and others, is that as we start to actually get GPUs and such out towards the edge, what really happens is that the edge becomes much more performant. We get better compute per watt. We can actually start learning directly at the edge and updating the models directly there. And this allows for very low latency, really dynamic orchestration now, not simply responding to a predetermined set of conditions, but actually dynamically reacting to real-time information and so on. And this becomes more and more important as the infrastructure is getting increasingly complex. So what that now starts to look like is something that you might call a software-defined grid. This is still very much subject to the physical limitations of what we have to do. There are still trucks that need to be rolled and so on. So this is not a simple problem. Varun pointed out, for example, that it's easy to shift load between sort of giant data centers. This is a much more complicated issue. So, however, we are, as usual, carefully deploying this in a collaboration, again, between the sort of cloud and the edge. Each is necessary, and neither is sufficient by itself. So what do I mean by this collaboration? You have the cloud and the edge. What the cloud now gets is improved visibility. So you can actually have very fine-grained information on PV, on storage, on EVs, and even sort of behind the meter in the premise. We have very fine-grained information on every grid element, so transformers, feeders, DER elements, and so on. We can get power flow, we can get operating envelope, we can get sort of where, any number of sort of data like that. Feed that up to the cloud for much better forecasting and planning. And then all of this also feeds into kind of resiliency solutions and longer-term planning in that sense. What is happening at the edge is that we have, as I said, dynamic orchestration, meaning that we can actually now orchestrate each grid element, again, transformers, feeders, and so on. We can manage EVs better, charge balancing, predictive charging. Same with PV and storage, better flow control, predictive charging, and so on, and build very large-scale, very fine-grained sort of demand response and VPP programs. A different way to think about this, or another way to think about it, is that what this increased intelligence at the edge gives you is a way to run essentially what you might think of as localized digital twins, kind of differentiating between, for example, what San Jose's piece of the grid operates as compared to the more sparse Central Valley or Lake Tahoe. Those kind of localized digital twins can then roll up to the master digital twins that are doing the longer term planning and so on. So what I've hoped I've motivated is that delivering energy to humans is a challenging task. It's a large-scale grid and very distributed and so on. But between the industry, NVIDIA, and ourselves, we're moving quite rapidly to try to improve the quality of service as soon as possible. Thank you for your attention.